Is the vision, development, and success of the Solar Mesosphere Explorer by Gary Rottman.
My name is Gary Rottman, and I first of all want to thank the organizing committee for inviting me to give this talk. It's something I'm very, very pleased to do. SME meant a lot to me. I know it meant a lot to Charles. I want to also thank the Barth family for participating in this, because this makes it a much fuller and more rewarding experience. The last talk Bill taught, I'm not going to use that green thing. Everybody thinks it's a circler and an underliner, but this is a building on campus. We call this the Space Science Building, and this is where it all started. This is where the scientists were, the students were, all of that back in the mid-70s. We also had a building out at 55th Street, possibly the ugliest building, and finally they've torn it down. But that's where the whole SME program ran on. Here I mean the vision of Charles Barth. I mean SME was really, I think, his vision of how to do science. So, excuse me, I'm going to run over here and push an arrow. This is part of Paul's talk. He didn't mention that Mariner 7, when it flew by Mars, it observed ozone. And that was the first measurement of ozone on Mars. And so then shortly after that, Mariner 9 is going to go. It's going to be the first satellite to go in orbit around the planet. And it's going to stay there for a while, and it's going to measure ozone. It's really going to try to understand what's going on ozone on Mars. And it found that ozone is highly variable. It found that it's strongly dependent on temperature, inversely proportional to temperature, and it's also inversely proportional to water vapor, not hydrogen. And there's a paper down at the bottom. I know several people worked on this. Charlie Horde, anybody with Mariner 9 worked on this issue. But I'm circling this one paper by Charles and Mary Dick. They came out in 1974. That's going to be a big year here. 74, we're going to concentrate on that. That was a year that everything was very different. We didn't even have, I don't think, overhead projectors. I think you had to make slides and put them in a carousel, and that's how you gave talks. You young people won't even understand. I'm going to talk about writing a proposal, and that meant you wrote it longhand. But in 74 also, these two gentlemen, Roland and Molina, came out with this very, very important paper. And they said that if we keep producing freons, fluorochloromethanes, and reducing them into the atmosphere, they're finding their way up into the stratosphere. They're going to stay there for 100 years and destroy ozone. And that got a lot of attention. It got a lot of attention by Congress, by the American people, because they were saying stop releasing freons. I read an article recently where it said Roland, these are chemists. After he put out that paper, for about 10 years, he was never invited to give another talk at any university. So this was a very controversial thing, and this happened in 74. And now, I see. Here's another gentleman. This is Sidney Chapman. Sidney was a British mathematician, gas kineticist, worked in England. When he retired in the mid-50s, he traveled around, a lot of time in Alaska, but he was also spent a lot of time in Boulder. And back in his early life, he came up with these reactions that are called the Chapman reactions. And now, I'm going to use a marker, but over here, you people follow over there. This says that if you have molecular oxygen in the atmosphere, the normal form of oxygen, sunlight with these wavelengths, this energetic sunlight, will break it into two oxygens. And one of those oxygens will go find an O2 and make an ozone. So that's a production mechanism. That's how ozone is made in the atmosphere. And then this is another reaction, and this is how it's destroyed in the atmosphere. The ozone, also hit by sunlight, dissociates, and then that goes back into molecular oxygen. So this is the basic reactions. They go on. They finally establish equilibrium, and that establishes an ozone layer up in the stratosphere. So the next slide then is an early slide. This is, it's jumping ahead. Don't worry about the fact that it's Solar Mesosphere Explorer. You're not supposed to know that yet. But if you run those reactions in the atmosphere, there's the distribution of ozone you get. Ozone is pretty complicated down here where most of the ozone is. That's where these freons are going to get in and start tearing it up. The upper side of this, though, should just be ozone being controlled by the sun. The sun is controlling how much ozone. If the sun changes, then you expect ozone to change. So this is a region that's simpler, but still had not been studied. I think people were saying it sure would be nice to have measurements of this, to have a satellite up there that would determine the changes in ozone due to the changes in solar radiation, but also if it's up there, it could just determine changes in ozone due to temperature, whatever's going on. So this is an idea of a satellite, and we're going to pursue this. Maybe this is some of Charles's vision, but I think Charles's vision would have been, wouldn't that be nice to have a satellite at Mars? And that's still waiting to happen, maybe an ozone satellite there. But also, now we're in 1974, NASA puts out an announcement of opportunity. This means this is an announcement. Anybody with good ideas, tell us your good ideas, and maybe we'll let you proceed with that. And so these are the guidelines of that announcement of opportunity. Unfortunately, at least if you wanted to do planetary, it said it had to either be astrophysics or solar terrestrial. It had to deal with the Earth or astrophysics. No planetary missions need apply. This was going to be an Explorer, so it was going to be managed by the Goddard Space Flight Center. Goddard Space Flight Center managed, that was the NASA center that managed all these programs. NASA will provide a launch on something called the Solid Controlled Orbital Utility Test System. You want to go on that? That's also known as a SCOUT, but that's what it is. It's 4 solid rockets put together. It's a very reliable. It had put a lot of missions into space, but it wasn't necessarily, it was more of the Model T ways of getting to orbit. Yeah, and then the guideline was you better have excellent, well-founded science objectives, and you had to be low cost. So Charles, at LASP, in that building I showed in the beginning, this is the selection of people in that building that he had to put together a team to write a proposal to do this. And I'm sorry that that's kind of out of focus. It's not your eyes. There's a handful of people in this room who are still here. Gary, Thomas, Karen, Sabina, Ian. But anyway, Charlie Horde. So these are the people that made up the team, and we had a meeting in a room, and we're going to write a proposal in response to this announcement of opportunity. I don't know what happened to Ron Thomas. I mean, he was here, and you can see his name belongs here, but maybe the letters fall out. These are one of those little pegboard type things. But anyway, that's the team that sat down and wrote this, except one other person that wasn't on that board. This is Julie London, who was, it looks like he was in the basement, but he was really, I think at that time, up in the Gamow Tower. Julie was an expert all the way back from the 50s in dealing with ozone in the atmosphere. He was extremely interested in this, so he joined this team and we wrote a proposal. So now let's go back to Chapman reactions. If you're going to be up in the mesosphere, there is a catalytic reactions going on that are destroying ozone, and they're all, I have to push the button again, I'm sorry. Did a lot of exercise up here. So this is water vapor, and it makes odd hydrogen. Now we're up in the mesosphere though, 50 to 90 kilometers up. And if you watch these reactions, and it's not necessarily what you can see, or you just follow this, that the odd hydrogen is destroying ozone. So that's going on. So the more water that there is, the less ozone you're going to expect. So we need to build a satellite to go do this. Well, I'm sorry, the other thing you would like to know about the atmosphere you're looking at is what about temperature and pressure. So with the UV type instruments that Charles had on the Mariner programs, on OGO, with UV, ultraviolet, you can measure the ozone. You imagine sunlight going into the atmosphere and coming back to your instrument. If there's any ozone along that path, it's going to absorb some of that radiation. So this is basically how that works. Paul Philman had talked a little bit earlier about in 1972, when I first came here, we flew this little 8-meter spectrometer on a rocket that was going to be part of the program to calibrate another instrument that the lab was doing, a orbiting solar observatory. But we flew that in 1972 in December in support of this mission that Bill Fassey had with Charles as a co-I, with Paul Feldman, Dick Henry, Warren Moose at Hopkins, Gary Thomas, I think you were on the Apollo thing. But anyway, we flew a little solar instrument and it got the first irradiance spectrum. This is the light from the sun, how much ultraviolet light is there. And that's what really started and established the irradiance program at LASP. I'm not going to talk about that, but that goes up all the way to why Tom Woods is not here, because he's down in White Sands getting to launch a rocket next Friday, I think. But another way of getting ozone is when these photons break apart the ozone, they make molecular oxygen, but it's in an excited state. And so to get back to its normal state, its ground state, it emits radiation in the infrared. So we have another instrument looking down in the infrared, and that's going to also tell us how much of this reaction is going on. But we're missing some things. We don't have much information about water vapor. We don't have information about temperature and pressure. Oh, by the way, it'd be nice to get another measurement of ozone. So we're going to build an infrared instrument, an infrared radiometer. This is a new instrument. This is not something that was in LASP Arsenal, but this is an infrared radiometer. Infrared detectors way in the infrared. And at a certain band, they measure ozone. At a certain band, they measure water vapor. And if you do it right with a couple bands in CO2, you can get temperature and pressure. Completely new instrument for LASP. And so now you need to know that if you have something new and nobody in LASP knows how to do it, you talk to George Lawrence. George Lawrence said, yeah, I can do that. That sounds easy. So then we have an infrared radiometer, and I'll just associate some names here. You know, Dave Rush is probably associated with the UVS, myself with this instrument, Ron Thomas with this, and now put George down there. Now there was one other instrument that measured NO2, and I'm not going to talk about that. So there's a fifth instrument on here, and that's measuring NO2, and that's something that George Mount was doing with John Noxon over at the Aeronomy Lab, and I don't have time to fully include that. All right, so now we're going to take those instruments and we're going to put it on a satellite, and we're going to put it in an orbit. And this is a polar orbit going over the poles. And so every day it'll pass, the Earth will kind of rotate down below it, you'll get full coverage of the Earth. But because we really are interested in the sun affecting ozone, we'd like it always to kind of be at the same angle for the sun hitting the atmosphere. So we'd like to stay in this orbit. And this is called a 3 p.m. orbit. In other words, the satellite's going to move from south to north at 3 o'clock in the afternoon. And then an hour and a half later, it's going to go over somebody else at 3 in the afternoon, but that's going to be a different longitude. The satellite's going to be spinning 5 revolutions per minute, so every 12 seconds it spins once. Your instruments look out, and they scan down through the limb. They make their measurements. They go down through the nadir, and then they come up and could look at the other limb as it goes out of the atmosphere. And I knew I had only been doing rocket things. I didn't understand this. I didn't even believe that you could do a lot of this. But, okay, and so to do that, the Earth is going around the sun. Some of us geocentricists think that the sun is moving 1 degree a day. So you better change that orbit 1 degree a day. And to move that orbit 1 degree a day, that's called precession of the orbit. You need to get just the right inclination. That is, this doesn't quite go over the pole. It goes a little bit on the other side of the pole at 97.5 degrees. And if you get just the right altitude, that orbit's going to precess at 1 degree a day. I didn't believe it either. So here's the last proposal. I don't know what happened. Oh, okay, there that put in some things. It says to do that, you need to get just the right circular orbit, you need to get just the right elevation, altitude, and you need to get just the right inclination. and we're going to go on a scout vehicle. When you write the proposal, you say, yeah, we're going to do all that. We're going to let Goddard manage this. We like that. We like the scout launch. You know, everything. That's writing the proposal. But I must say we were concerned about the scout launch, because when you really looked at the tables, you weren't maybe going to get that right altitude. You maybe weren't going to get a circular orbit. And when you worked all that together, it was going to be hard to do this. All right, and let me go now. These are the instruments that are on there. I'm not going to go through this except to tell you, out of those 5 I've highlighted in red, 4 of those are this magic Ebert-Fasti spectrometer. I'm going to alert you if we ever use a different spectrometer, so just assume they're all Ebert-Fastis, except that this infrared radiometer right here is a different type of instrument. And then down at the bottom it says that the satellite will be spin stabilized. That's what's going to keep it stable. It's going to use 2 limb sensors, kind of looking out along forward and back of the spin axis, so they're kind of coning. It's kind of like looking at these 2 screens up here. As they pass down across the Earth, you can use that to determine what the spin rate is, and you can determine if the satellite is tilting one way or the other. And then it says, and there will be an autonomous attitude control. That means whoever does the spacecraft is going to know how to make an algorithm. Is that who? Okay. To do this. I'm going to go over this one real quick because we've already seen that several times. And now let me go to this. These are what I'll call the markups on the proposal. So yes, it's going to be solar terrestrial. I should mention, in response to this, there were 175 proposals submitted. And there were 4 astrophysics selected and 4 solar terrestrial. And we were one of the category 1 solar terrestrial to measure ozone. But Charles had a long history going back to JPL, and I don't know how this happened. Jim Stewart's going to talk in a bit. He's from JPL. He was kind of a deputy program manager. But there's a lot of finagling going on to move a program from Goddard, who had done the Explorers, and get it out to JPL. But sure enough, Charles did that. And so in '76, just shortly, a year or so after, the program management was moved to JPL. Luck be told, that Scout was replaced by a Delta. So this is going from a Model T to a Cadillac. I mean, the Delta is going to put us right in the right orbit that we need to be in. Well, and then I guess the other ones, by this time it's going to be managed in a PI mode, and that the control center is going to be here at LASP, just as Bill has told us. So then we go out for bids in the spacecraft, and we pick Ball Brothers. So now these are all the instruments, and these are, this is the bus that Ball Brothers out to Arapahoe is going to build. We're going to put these together. Ball was selected in '79, and that's a spacecraft design that they came up with. And the reason they could do that is here is the Delta. I mean, this satellite SME is like a pea in a pod. I mean, it's you could put several of these satellites in the shroud. And what Ball did is a very clever thing is to save money on this. They could throw weight at it. This thing could be as heavy as it wanted. This Delta, like I said, could put a lot more into orbit. So that's the spacecraft, and I'm going to move kind of quickly here because Larry keeps waving fingers at me. This is not a screen from SME, but that's what SME did. The Control Center came up with these screens, and those colors aren't just nice. All the data coming from the satellite are being checked against certain ranges. And if they're out of that range, they come up in red. If they're in the range, they come up in green. And there was even a little bit wider range, and that would be yellow. So the operator, these students sitting at the control thing, all they needed to do was look and make sure there was no red. And we were all looking there at launch, and everything was green, except I picked this one because it has a couple red, 1 or 2 red. But you look at what that red is, and it's a temperature. Temperatures, we can get that under control. But when you go to the temperature page, almost all the things on the instrument side, on the observatory side of the spacecraft are red. And they're getting cold, and they're getting colder and colder and colder. I mean, we're talking minus 60 degrees. The instruments have never been tested there. And I can remember a ball mechanical engineer saying, it can't be that cold. If it gets that cold, the 4 bolts that hold the two together will snap. Well, that's not an encouraging thing, but we had to warm the spacecraft up. So here's the spin axis of the spacecraft. This is what I call the beta angle. That's the angle the sun's coming in. Remember, the spacecraft is just flying the way it's supposed to. But lo and behold, if you can change that beta angle, change the angle the sun comes in, you can get more sunlight on the back end. You see the observatory, it's a lot of black and gold. That's not because of CU, but that's the thermal design. That's supposed to be the different types of coating you put on to get the temperature just right. So we're going to have to change the beta angle. We're going to switch off the automatic control, and we're going to go to manual mode controlling this. Not too big of a problem for solar, or for the energy, the solar power it's getting, but a big problem now because it's not going to keep track of its attitude and keep steering itself. So who's going to do this? Not me. Because I'm not sure I believed it in the beginning. But Charles is the one that led it. I think Charles got, remember George Lawrence? We can do this. I can help figure this out. John Calley, who was the attitude control person, and Tom Sparn, who is here, was a student then, a graduate student, but now has gone on to be program managers and everything else at LASP. So they got together. They're going to manually steer this thing, and this is about a day and a half or 2 days after launch. Real scary stuff. All right, I'm going to go very quickly. This is a science, and this is probably what I was supposed to tell you all about. Measure ozone with 2 different instruments. They agree very well, but they always measure ozone quite a bit higher than the models. And so what's wrong? Well, finally the modelers got their act together and the reaction rates and so on and so forth, and they get agreement. I'm going to just pass over the slide. This thing says you measure solar radiation, and you see how the ozone changes in response to that. We did that. Here's solar radiation during the whole mission. The sun's very active. Then the sun got very quiet, very active again. This is an 11-year solar cycle. But I'm going to point out here some times where we have a 27-day period of the sun. That's the rotation period of the sun. So the signal is very nice. This is like a searchlight. Every 27 days coming around. So here's that sun light in a certain wavelength. In that period, you can see the 27-day variation. And here's the ozone. And what do you think? That looks pretty good. The agreement, something's going on there. The sun and the ozone seem to be behaving very well together. But if you look close, it seems that I probably got the 2 plots mixed up. Because the ozone is leading the sun. So now we have something where the ozone is causing the sun to change. But not to worry. Richard Ekman, I put in these little boxes down here, last people that worked on this, but when you put the temperature feedback and everything in, it behaves just properly. It's just what you want. And I don't have time to explain that, so we'll go on. Gary Thomas and John Olivero were working with polar mesospheric clouds because SME could look at it ahead, and then after it got behind, it could look at it behind. That's called a phase angle change of the illumination, and because there's a couple wavelengths with that, you can come up with a particle size of polar mesospheric clouds. Again, I'm not going to talk about NO2. I'm real sorry about that. Solar proton events in the summer of '82, a big proton flare happened on the sun, and we saw the reduction in ozone as a result of that. And then lucky for us, in '82, there was a very large volcano down in Mexico, El Chachon. A number of papers were written about that. That's now aerosols being dumped in the atmosphere. Joe Zawadny, who was a student working on NO2, I don't know that he ever really worked on El Chachon, but he's looking at the NO2 signal and he says, the temperature is just dropped by 100 Kelvin. And that was quite shocking. I think that was the first I'd heard about it. And then somebody said, no, there was a volcano down in Mexico. Okay, I'm gonna leave it here. And this is just a quote I found in one of the documents led by Charles Barth, the SMA program. Most effectively demonstrated the capacity of LASP and the university to manage space programs. And we've done lots of space programs, so that's it.
Question?
I feel like Brian Williams now. How good is my history? Fact checking. People are going to say it didn't happen that way. You were never there.
Jeremy?
Just a comment that we can do it. Measuring water vapor in the mesosphere at 6.2 microns is super difficult. And I don't think ever got anything very good from SME, but it's also extremely difficult with, 20 years later, knowledge and everything else to get it. So there's a lot of non-LTE and other things next day. So it's not simple. It sounds simple when you first think about it.
Well, I make everything sound simple. It's not.
So, Dan Baker.
Yeah, did all 8 of those AO7, I guess it was AO6 and 7 that elicited all those things, right? Did all of those fly?
No. And what you learn with NASA, and Dan, I know you know this, if they pick 4, you better be the first one.
Yeah, right.
Because it's very unlikely money is going to go all the way down. There was another one on the astrophysics side is Stu Boyer's EUVE, and that one also finally flew at least 10 years later.
Yeah.
And that was also managed by JPL. On the other side, Kobe, these are now Goddard ones, finally flew, but again, after a long time, and I don't know the other ones. I think you can't even Google some of them.
As I pointed out at varying times, if you look at SME, it came right at the end of the golden period of explorers and right before the great explorer drought. If you look from the beginning of Explorer 1 to SME, there's a launch rate of explorers about 2.5 per year. During the entire time that SME was in orbit, 8 years, there were only 2 Explorer missions. And it wasn't until well after SME had gone in that the Explorer program picked up again under Dan Golden. But there was a very serious drought of Explorer opportunities during that period.
So I just wanted to say one thing. I was here at that time listening to all these interesting things about these Ebert-Fasty spectrometers, observing the effect of volcanoes on the Earth's atmosphere, and at the same time Pioneer Venus had another Ebert spectrometer that was orbiting Venus, and we saw some similar stuff that encouraged us to imagine that there were volcanoes at that time erupting on Venus, a question that's still open. So after hearing about SME, there's another heritage of that, we applied some of that information to the other planets. Okay, let's call for the next talk. Thanks, Gary.